these mics. Okay, so now I'm going to talk about cache coherency. So as I said, caches are quite complicated on their own, but when you think, it only takes a few seconds thought to realize when you have multiple processes attached to the same memory with multiple caches, it gets really horrible. So a symmetric multiprocessor is your canonical, theoretical view of what a multiprocessor, multi-core machine looks like. The idea is you have a bunch of processors, 1, 2, 3, 4, 5, 6 here, connected to memory. They're all connected to the same memory. And this is, they share some connection to memory through some shared bus. And in this model, there's no processor is special. So in your canonical idea of a shared symmetric multiprocessor, an SMP, every process has the same access times to memory. Now, of course, it's not like that, and these examples are very old examples, actually. But, of course, nowadays, your canonical example of this is your laptop. You have more than one core in your laptop, all connected to the same memory. So actually, symmetric multiprocessor, SMP, has been around for a long time. I don't know, but 10 years ago, if you bought a server for your department, it would be an SMP. But what would happen is somebody would buy 1, 2, 3, 4, 5, 6 single-core chips. They used to exist, single-core chips. And they would build some motherboard with 6 sockets, and they would do all this wiring, and they'd plug 6 chips in. So basically, the processors were single-core processors, okay? And somebody else added all this stuff externally. So they just bought the processors, and they did all this stuff external to the so there would be 6 sockets on the board, 6 chips, and all this stuff was done externally. As manufacturing processes have got better, it's now possible and desirable to place multiple processes on a chip. The cores are so small, you can actually put more than one on a single piece of silicon. So from a programmer, this is not relevant. From a programmer, there's no difference between programming in principle, a multi-core, an old-fashioned multi-core symmetric SMP machine versus a modern multi-core processor. It just means that all the speeds are quicker and the feeds, the latencies are lower, the bandwidths are higher. But as a programming model, it's been around for a long time. So OpenMP was around a long time ago for SMP processors before there was any such thing as a multi-core chip. The main difference is that now processors can share caches because their cores are put on the same piece of silicon. They can share caches. And what typically happens is each core has its own level 1 and level 2 cache, but level 3 cache is shared. That's a standard sort of model. So this is a sort of a very naive view of what it might look like, that you each have 4 CPUs, each one has its L1 cache, each one has a slightly larger L2 cache. They share an L3 cache, and then you have main memory. And the important point about this is if you run once this architecture came around, single core benchmarks became meaningless because it wasn't clear what you meant. Because if you run a single core benchmark here, you're not running anything here. It has a very big L3 cache, so you get good performance. But in fact, in reality, you'd be running all 4 of them. They'd have a smaller L3 cache. So they didn't become meaningless, but single core benchmarks became even harder to interpret than they used to be because that core has access to more than its fair share of the resources. In reality, this is a bunch of pictures, a wee bit old, what they look like, but here's a Power 4 2-core chip. So there's 2 cores here. Something slightly weird going on with the cache. It was a bit weird. That's not an easy one to interpret. The Nehalem's quite easy to see. Quad-core chip. I mean, I'm not a circuit designer. But even I can spot there are 4 chips on this. It's 1, 2, 3, 4. They just look the same. They've each got some level 1 and some level 2, and the level 3 cache is shared. Physically, it's distributed, but logically, it's shared between them. So this is exactly, well, almost exactly the same picture as this one. Private L1, private L2, and a shared L3 with 4 cores. So that's the Nehalem from, I don't know when that was, 5 years ago. Sorry, I don't keep up, I'm not very up to date. Power 7, very modern, recently released 8-core chip. Again, 1, 2, 3, 4, 5, 6, 7, 8, each with their own L2 cache and a shared L3. So the important point is these two cores can communicate with each other without going out to main memory because they can do it through the L3 cache. So they don't have to go off processor to do it. So, as I said, multiple cores can communicate, but we do have this problem that cores can contend for space in the shared cache. So it's actually quite hard to predict exactly what's going to happen, because you're sharing the cache with other cores. You might say, it's okay, I've got a 4-way associative cache. I know I'm only ever going to load 4 cache lines into the same set, but maybe somebody else is doing it at the same time. So what basically happens is, in practice, these nice graphs you used to get, which went like this, were very clear and jagged, now all become smoothed out and slightly harder to interpret. Things are a bit fuzzier now. The main point, though, is they have to share off-chip bandwidth for access to main memory. That is the main point. So you'll have seen that, again, not only if you did a single core benchmark previously, not only did it have all the L3 cache, it was the only guy using this bus to main memory. That's unrealistic, because in a real code, these guys will be doing it as well. So you're going to have to worry that, is this bus fast enough to keep up with all these 4 guys going flat out? Probably not. So the simplest way to build a small-scale parallel machine is to connect multiple processors to a single memory, true shared memory. So my previous diagram, sorry, I'm jumping about, that's the problem from having different, this was my canonical view, a number of processors and memory. Of course, that's not what happens, because each processor has its own cache. So what it really looks like is this, processor, cache. And then what's happening is, each processor will individually cache transactions from memory. And if 2 processors have their own copy of the same data in memory, and then one updates it, what's going to happen? Because one guy's got one value, one guy's got another. How does he know that that someone has updated the data value? It gets very complicated. So if you build a multiprocessor system, the main problem is you have to keep the caches coherent. You have to know that if you read that your data in cache is always valid, or if it's not valid, you know it's not valid, and you know you have to go out to main memory again. Because when we program in the shared memory programming model, like if you're doing OpenMP or threads, we assume that shared variables have a unique value. Now in practice, they're replicated across different caches, but the programming model has to ensure that there's logically only a single value. So to avoid 2 processors caching different values of the same memory location, caches must be kept coherent. So they're coherent with each other. And the most important point is, if I update a value, it must cause all the other copies of this location to be removed from the caches. So if all of us read a value into memory and we cache it, if I update it, you have to be told it's changed. Either told what the new value is, or told that your value is out of date and you have to go to main memory and get it again. And that is the bottleneck with building shared memory systems, that keeping the caches coherent, or as well as being difficult to maintain enough memory bandwidth to satisfy all the cores, it's the overhead of keeping all the caches coherent, which means that you can't build very large shared memory systems. Well, of course, SGI built, we'll come to distributed, SGI did build up to sort of 256 and bigger shared memory systems, but it's very difficult to build. There are more. I don't know how. We're interested to hear how the Intel mic has solved it, but there are real issues that come about when you have to keep tens, dozens of caches coherent. So what we have to do is, not only do we have to store a value in cache, we have to store additional information about who else has that value. Is it up to date? What's its status? Has this block been modified? Is this block stored in more than one cache? Because if it is, then if I update it, I have to tell somebody. And there are 2 types of protocol which can implement this. And I'll go through this one in some detail. Snoopy protocols or directory-based. So what happens with Snoopy protocols is everybody sees everything. So it's like me, every time I update a value in cache, I shout out, I've updated value 53. And if you've got value 53, it's up to you to make sure that you put a cross by it saying that one's out of date, okay? So in a Snoopy protocol, the idea is that you're all snooping on the bus. But basically, it's up to you to make sure every core monitors all the memory traffic. And if it's relevant to it, oh, he's updating that value. It's up to that core to update its stuff locally. So all the cores, all the processors monitor all the memory traffic all the time to try and keep everything up to date. There's no central status. All processors see every request. Now, we'll come back to directory-based later, but to see it, this is surprisingly complicated. It seems quite simple in practice. You say, like, every time anyone makes a memory request, everybody knows about it, and it's up to them to act accordingly. But what are we going to do? Well, we have to be able to invalidate cache lines. You have to be able to say, this value in the cache is no longer valid. Okay? Well, we already have a valid tag. Previously, we just used it to indicate whether data had been loaded or not. But we could just set it to invalid to indicate, well, it was loaded, but now it's not relevant. But we also need an extra bit to indicate the sharing status. We need to know whether I'm the only person that has this cache line or if other people have it as well. And there's lots of implementations of this, but the main model is, as I said, all processors monitor all bus transactions. Whenever anyone makes any memory request, it's effectively broadcast to everybody. Everybody keeps an eye on what's going on. If they see an invalidation message on the bus, they have to say, somebody's saying memory location 53 is no longer valid. You have to say, do I have that? Yes, I better invalidate it. Also, if someone makes a read request and I have it, I have to give that to them. I say, well, I've updated that. I better give them. They better not get it from memory because the memory is not valid. I better give them that value. And it's actually quite useful to go through a very, very simple three-state example just to see how it works. So I don't know if this is possibly the simplest example you can imagine. So each cache line has three states. Okay? Each cache block line can exist in one of three states. Modified, okay? It's the only valid copy in any cache, and its value is different from that in memory. So I've read a cache line, I've modified it, but nobody else has read that cache line. Shared says it's a valid copy. In other words, it's the same as the value in memory, but other people also may have it. And invalid says it's out of date. Invalid says, well, I've got this copy in my cache, but somebody else has updated that value, and so I'm going to have to reload it. And so if we go through what happens, the processor can only do two things. It can read or write, processor read or processor write. But what I'm doing is the processor is issuing those requests to the memory system, the memory bus, and the memory bus can do three things. It can read exclusive, which means it's going to modify it, or it can flush to memory. And it's probably good if we go through a specific example. I hope I can get this right. So we've got three processors, and we've only got one piece. For simplicity, we've just got one data value. We'll call it value. So R1 means a read by processor 1. W3 means a write by processor 3. And we'll just think about one value. Okay, we're not bothering about multiple cache lines. We've just got one value. And we'll read through what happens if processor 1 reads, processor 2 reads, processor 3 writes, processor 2 reads, processor 1 writes, this whole gory detail. But it's worth going through to see what happens. Now, this is a I believe, this is possibly the simplest protocol you can imagine. And even with this protocol, you can see it gets quite complicated. So, processor 1 wants to read the data. That's our first thing. So processor 1, so here's each processor, here's its value in the cache, and here's the main memory, and here's our bus. It's a cold start. The cache doesn't have it. I generate a bus read. The memory controller provides the data. The data goes into the cache in the shared state. So this is just our normal view of what would happen in a single processor example. I want to read data. It's not in cache. It's read from the memory. It's put into the cache. Shared, remember, means that there may be multiple versions of this, but shared means that its value is the same as in main memory. It's just been read. Okay, that's quite simple. Processor 2 wants to read the value. Its cache doesn't have the data. It places a bus read to notify the processor and ask for the data. The memory controller provides the data. Again, processor 1 will see that, but it will say, well, I don't care. He's just reading the same value as me, so I don't have to do anything. So that's quite simple. That's not a problem. The first problem comes when processor 3 wants to write the value. Okay? So this is what's happening is both processor 1 and processor 2 have the value in their cache. It's the same as the value. Oh, actually, sorry. In this one, it's not obvious, but sorry, processor 2 wants to read the value. It asks for it, it gets it from memory. It could have, in principle, got it from processor 1, from the cache. But because it's a shared state, we know that that value and that value are the same, so it gets it from the memory. It's just the simplest thing to do. So the first problem comes with processor wants to write. So it wants to write, okay? Because it wants to write, remember there's no such thing as writing when you're writing to the cache. What it's going to do is the memory controller says, well, I want to write it, and I don't have the value, so I have to read it, and it's going to do a read exclusive, means I'm going to modify it. So it does a bus read exclusive, which says, I want to read this value, and I'm going to modify it. So immediately, processor 1 and processor C know that processor 1 and processor 2 know that processor 3 has done a read exclusive. They immediately invalidate their values. They say, well, somebody else has grabbed this, and they're going to modify it. I better scratch off my values. They're scratched off, and then the data comes from the main memory. So now we have an invalid cache line, an invalid cache line, and a modified cache line in processor 3. Next, processor 2 wants to read the value, okay? It says it wants to read. Processor 3's cache is the most up-to-date value. So what happens is processor 3 actually provides the value. So this read is actually cancelled. Processor 2 issues a read, and the memory system says, okay, and you want to read, but you don't really want to read because I know processor 3 has got it. So processor 3 gives it the value. And in this simple model, it flushes it to main memory. In this model, you're never allowed to have more than one cache line with a modified value. So what it does is it flushes it to main memory to keep the memory consistent. Okay? So what's happened here is, as I said, processor 2 wants to read it. Processor 3 has an updated value in its cache that's provided via the bus, but it's actually processor 2, and then processor 3 also flushes the data to main memory. Okay. And then we can go on. I think this is, again, processor 1 wants to read the data. We get the same kind of thing. We have to invalidate these values wants to write, again, the same thing happens. Processor 1 has to do a read exclusive, modify that value, and these guys have to scratch out their values. And then we can carry on. I mean, I think what these diagrams show is even in the most simple possible cache coherence protocol, you get a simple action has a lot of effects, okay? This guy just wants to write some data, but it has a value, it goes there, and this is invalidated, and this is scratched. It all gets very complicated. And I think what you'll see is also there's an awful lot of memory traffic going on. So I won't go through all the, well, the final one is only the, okay. The final one is the processor who wants to read the value. Its cache has an up-to-date copy. No bus transaction needs to take place if there's no cache miss. This is what we'd like to happen all the time. We'd like people to be reading data from their cache, not having all this horrible bus traffic. But you can see things get very complicated. And so the way you can represent this is you have 3 states for the cache, which is modified, shared, and invalid. And various read and write operations cause the cache line to modify its state. So you have a state, you have transitions between these 3 states, and the transition paths depend on what the action is. Now, I did see there's some textbook, I can't remember what the book is, which had the full state diagram for the Origin 2000, which was a large shared memory machine. Well, it was actually distributed shared memory, but I've seen these diagrams for real machines, and they're just horrific. You know, they're pages and pages and pages of stuff and corner cases. So you can see this is obviously not a very efficient thing. You can see you could immediately improve it, okay? You can improve it by saying, you can say I have an exclusive state. This copy has not been modified, but it's the only copy at any cache. And then you know that if you want to modify it, then you're happy. You don't need to tell anybody. This copy has been modified, but there are maybe other copies in a shared state. So you can in our model, if a data that had been modified, basically nobody else was even allowed to have it shared. They had to be invalidated. So you can, these are called MESI and MOESI. So these are the real ones. But as a mental model, if you want to have a model in your mind of how cache coherency protocols work, this simple one of of MSI is a useful model to have in your mind for the kind of things that go on. Of course, in practice, it's more complicated, but this is a very useful sort of base model to have. So what are the implications for this? Well, there are a number of implications. I go back to the immediate. The first implication is that all these guys share the bus. So if you measure memory bandwidth on one processor as a gigabyte a second, if all 6 go, you're probably not going to get 6 gigabytes a second, because this might only be able to support 2 gigabytes a second, for example. So if you measure the memory bandwidth from a single processor or core, you get an inflated value. So it's often useful to run memory bandwidth tests with all the processors going flat out. So that's a fairly obvious thing that's going to happen with multiple cores. You're sharing the bandwidth. The second thing that happens is you're sharing the L3 cache. So when you do that if you do the bandwidth test with multiple cores, not only will the values be less, but the steps might be in different places, because here effectively the L3 cache will be a quarter of the size. So you might see the steps in different places because effectively the cache sizes have changed. But the thing which really kills you can really kill you with these coherency protocols is false sharing. So it's absolutely clear that if 2 processes simultaneously write to the same value, you've got problems, okay? If one process writes the value A, okay, it invalidates the cache in process B, and then if process B writes the value A, it has to be read over. If you think about it, if two processes or 2 threads flip-flop in terms of updating a value, the entire cache line is going to be transitioning, bouncing backwards and forwards between these two threads, okay? And that's a bad thing to happen. However, if you're updating the same value from 2 different threads, that's your fault, okay? You shouldn't be doing that. That's easy to see from the program, yeah? You know, the thread. But the problem is that the coherency is done on a cache line which is bigger than a variable. So you can get a point, you can have a situation where you have 2 variables, A and B, in your program. Thread 1 is updating A, thread 2 is updating B. From the program, it looks like there's no problem. A and B are different variables. There can be no cache problems here. But if A and B live in the same cache line, there's a problem. Because I update A, which also, because the updates are done on a cache line basis, invalidates the value for B. So it cannot be entirely obvious from looking at your program if 2 threads have cache conflicts, because it can depend on whether the variables live in the same cache line. Now, in practice, scalars and things won't live in the same cache line. The OS, the compiler, will spread them out. But if you're updating different parts of an array, you can get problems. And it can be quite hard to detect. So this is just, the coherency is done on 64 or 128 bytes. We saw that on the Interlagos, it's 64 bytes. This can cause a thing called false sharing. 2 processors write the different words on the same cache line, okay? So each write will invalidate the copy of the cache, and you get lots of bus traffic. So it can be a significant performance problem in threaded programs, and it can be quite difficult to detect. And where you see this most often is people, if people are writing a threaded program, they want to add up a big array, okay? So they say, well, I'll get thread 1 to add up the first half of the array, and thread 2 to add up the second half of the array. Fine. You declare a little array, subsum of 2 with 2 values, and thread 1 updates the first value of the array, and thread 2 updates the second value, okay? You've got a little array where you want to put the values from all the different threads, and you've stuck them together. So almost by definition, consecutive values in that array will live in the same cache line. And you get some false sharing problems there. And there's a small example, slightly contrived, well, contorted, but in the examples I've handed out, which effectively does that. What it does is it does simultaneous updates of 2 values, and it starts updating them this far apart, and it moves them closer and closer and closer together till they hit the same cache line, and you see the performance drop, and then you see it. So you can see how big the cache line is by looking at the performance of this loop as a function of the separation between these 2 variables. And hopefully we'll get the same answer, 64 bytes, as we did. Yeah, hopefully we'll get the same answer. And it's difficult to detect because it's not immediately obvious looking at the program source that you're doing this. Okay, so first exercise is slightly off. What I want you to do is really to basically to do this saturating the memory bandwidth thing. So I want you to run 32 copies of the cache of the cache program. The way to do this is actually running 32 processes. Okay, so the other examples use threads, but you can, if you have a serial code and you want to run 32 copies of it, you can just do this. And on the cray, each one of these processes is placed on a different core. So it's fine. We're doing what we want here. I tried to write this example using threads, and it didn't do what I expected. So I went back to the only disadvantage of this is you get vast amounts of screen output because you get 32 times the screen output you wanted. So you need to put it into a file. But this is useful. This will give you a feeling for what. So what do you expect the performance to be? So what do you expect? How do you expect the performance to be effective for small values of n, for small values of the problem size, by running multiple ones together? So we used to get 24 gigabytes a second. Will we still get 24 or not? Or we would expect to still get 24 because for small values it fits in the cache, and each process has its own cache. Now, on the Interlagos, it's not quite that clear because cores 0 and 1 are not really separate cores. But to first approximation, for small values of n, you will still get the same high bandwidth. But then for large values of n, we'll start to hit the bus. So for large values of n, we'll expect that the aggregate memory bandwidth to drop quite a bit. And also, the drop will happen earlier because we won't be benefited so much by L3, because all 32 cores will be sharing the same L3. So not only will the drop will happen earlier, and it will go deeper. So the question is, if a single core can saturate the memory bandwidth, then we're really, we don't know. The question, we don't know what the maximum memory bandwidth is at the moment. We got something like 8 gigabytes a second for large arrays. That's what we about 8 or something like that. So we know the memory bandwidth is at least 8. It could be as little as 8 because maybe a single core can saturate it. Hopefully it's more than 8. I can't quite remember what the numbers are. And then the next thing is actually to, I actually have a parallel version of the cache which uses OpenMP and a reduction, and you can run it using different numbers of threads and different thread placements. This is a bit more, this probably has more relevance when we talk about NUMA, but you can play around with that. But also in this section there's a specific false sharing example which you can run. Again, the only point here is when you run this, you have to do, when you run the code for the false sharing, make sure that you place the 2 threads on cores 0 and 2. Because cores 0 and 1 on the Interlagos aren't really, they're not SMT cores, but they share a floating point unit, put it that way. Cores 0, so it's all very weird. So put them on cores 0 and 2, okay, with the -CC option. And then you will be able to determine the cache line size from the coherency overheads, and hopefully we'll get the same value as we got before. I mean, I'm not a circuit designer. But even I can spot there are 4 chips on this. It's 1, 2, 3, 4. They just look the same. They've each got some level 1 and some level 2, and the level 3 cache is shared. Physically, it's distributed, but logically, it's shared between them. So this is exactly, well, almost exactly the same picture as this one. Private L1, private L2, and a shared L3 with 4 cores. So that's the Nehalem from, I don't know when that was, 5 years ago. Sorry, I don't keep up, I'm not very up to date with. Power 7, very modern, recently released 8-core chip. Again, 1, 2, 3, 4, 5, 6, 7, 8. Each with their own L2 cache and a shared L3. So the important point is these 2 cores can communicate with each other without going out to main memory because they can do it through the L3 cache. So they don't have to go off processor to do it. So CPUs, each one has its L1 cache, each one has a slightly larger L2 cache. They share an L3 cache, and then you have main memory. And the important point about this is if you run so once this architecture came around, single core benchmarks became meaningless because it wasn't clear what you meant. Because if you run a single core benchmark here, you're not running anything here. It has a very big L3 cache. so you get good performance. But in fact, in reality, you'd be running all 4 of them, they'd have a smaller L3 cache. So they didn't become meaningless, but single core benchmarks became even harder to interpret than they used to be because that core has access to more than its fair share of the resources. In reality, this is a bunch of pictures, a wee bit old, what they look like, but here's a Power 4 2-core chip, so there's 2 cores here. Something slightly weird going on with the cache. It was a bit weird. That's not an easy one to interpret. The Nehalem's quite easy to see. Quad-core chip on a chip. The cores are so small, you can actually put more than one on a single piece of silicon. So from a programmer, this is not relevant. From a programmer, there's no difference between programming, in principle, a multi-core, an old-fashioned multi-core symmetric SMP machine versus a modern multi-core processor. It just means that all the speeds are quicker and the feeds, the latencies are lower, the bandwidths are higher. But as a programming model, it's been around for a long time. So OpenMP was around a long time ago for SMP processors before there was any such thing as a multi-core chip. The main difference is that now processors can share caches because their cores are put on the same piece of silicon, they can share caches. And what typically happens is each core has its own level 1 and level 2 cache, but level 3 cache is shared. That's a standard sort of model. So this is a sort of a very naive view of what it might look like, that you each have 4 these mics. Okay, so now I'm going to talk about cache coherency. So as I said, caches are quite complicated on their own, but when you think, it only takes a few seconds thought to realize when you have multiple processes attached to the same memory with multiple caches, it gets really horrible. So a symmetric multiprocessor is your canonical, theoretical view of what a multiprocessor, multi-core machine looks like. The idea is you have a bunch of processors, 1, 2, 3, 4, 5, 6 here, connected to memory. They're all connected to the same memory, and this is they share some connection to memory through some shared bus. And in this model, there's no processor is special. So in your canonical idea of a shared symmetric multiprocessor, an SMP, every process has the same access times to memory. Now, of course, it's not like that, and these examples are very old examples, actually. But, of course, nowadays, your canonical example of this is your laptop. You have more than one core in your laptop, all connected to the same memory. So actually, symmetric multiprocessing, SMP, has been around for a long time. I don't know, but 10 years ago, if you bought a server for your department, it would be an SMP. But what would happen is somebody would buy 1, 2, 3, 4, 5, 6 single-core chips. They used to exist, single-core chips. And they would build some motherboard with 6 sockets, and they would do all this wiring, and they'd plug 6 chips in. So basically, the processors were single-core processors, okay? And somebody else added all this stuff externally. So they just bought the processors, and they did all this stuff external to the so there would be 6 sockets on the board, 6 chips, and all this stuff was done externally. As manufacturing processes have got better, it's now possible and desirable to place multiple processes